In this session, a few things that we've already done come together. This session is going to focus on matrix equations. Before we do that, I want to focus on numerical equations. For instance, if we had x plus 3 is equal to 5, then I would subtract 3 from both sides, and that would leave me with x plus 0 on the left-hand side and 2 on the right. And what I've done is I've performed the inverse of addition, right, by subtracting 3. And whatever we do to one side, we have to do to the other. In the context of multiplication, if we had, say, 3x is equal to 15, then I could multiply both sides of that equation by 1/3 and end up with, on the left-hand side, 1 times x is equal to 5. And in so doing, I would be doing the basically the inverse of multiplying by 3, right? Dividing by 3, or also known as multiplying by 1/3. In each case, I end up with an identity element. 0 is the identity element for addition. 1 is the identity element for multiplication. And to obtain those two, I use the additive inverse of 3 and the multiplicative inverse of 3, respectively. We're going to do basically the same thing, but in the context of matrices. If I had an equation, a matrix equation, of the form AX equals B, and I wanted to isolate the variable matrix X, what I would need to do is multiply on the left-hand side by something that would turn A, the coefficient, into the identity matrix. In other words, I would want to divide by A, but I can't, and so I'm going to multiply by the inverse of A inverse. Because matrix multiplication is not commutative, if I multiply the left-hand side by A inverse on the left, then I have to multiply the right-hand side by A inverse again on the left. A inverse times A is going to give me the identity matrix. So on the left-hand side, I'd have identity matrix times X, and on the right-hand side, I'd have A inverse times B. Because the identity matrix is what it is, on the left-hand side, the identity matrix times X would simply give me X. And so ultimately, X would be the product of A inverse times B if I started out with the matrix equation AX equals B. In other words, our pattern here is going to be to express a system of equations, that's the context we're going to be in, as a matrix equation, the coefficient matrix of which is going to be A. Find A inverse, and then multiply A inverse times B in order to get what X is. This seems a little weird to talk about in the abstract, so let's get to it. Express the system as a matrix equation of the form AX equals B, and then solve the system using the inverse of a matrix if possible. Our system is 2x minus 5y equals 15, 3x minus 6y equals 36. As you may recall, expressing this as a matrix equation means we're going to write down the coefficients 2, -5, 3, -6, and then a column variable matrix x, y, and that's going to equal the constant matrix 15, 36. And we now have this expressed in the form AX equals B. Since A is 2, -5, 3, -6, and we want to find its inverse, what we're going to do is we're going to set up an augmented matrix. 2, -5, 3, -6 in a vertical line, and then 1, 0, 0, 1, and perform row operations. At this point, I'm going to refer you to the video called Inverses of Matrices, where we actually found the inverse of this matrix. And after performing row operations, we end up with, on the left, 1, 0, 0, 1, and on the right, -2, 5/3, -1, 2/3. Again, for the steps on how that happened, a previous video. what we see here, though, is that A inverse then is the matrix on the right of the augmented matrix, -2, 5/3, -1, 2/3. Therefore, since our steps are essentially going to be to multiply by A inverse on the left and right, and on the left we end up with the identity matrix, we're going to get to write down that the column matrix xy is equal to A inverse, which is -2, 5/3, -1, 2/3, times the constant matrix 15, 36. So you see how that works? I hope you do. If not, I swear, rewind the thing and watch again. It'll eventually click. Hey, look, on the right-hand side, I have this matrix multiplication that's indicated. And so xy is equal to the product of A inverse and B. And so now we're back in that familiar territory where I'm going to take the first row, -2, 5/3, and multiply it by the column 15, 36. I do so entry by entry, and then I add. So -2 times 15 is -30. 5/3 times 36 is 60, and I add those two together. Then I take the second row, -1, 2/3, and multiply it by 15, 36. -1 times 15 is -15. 2/3 times 36 is 24, and then I add those two together. I end up with the column matrix xy is equal to the column matrix 39. If two matrices are equal, that means all their entries are equal. What we can conclude here is that the ordered pair xy is equal to the ordered pair 30, 9. I know that I wanted to express it that way because this was a system of equations. And folks, this is how we can use inverses of matrices to solve systems of equations. Of course, to check your answer, you would put 30 and 9 in place of x and y, respectively, in both of the original equations. Next, our system is -3x plus 1/2 y equals 2, 6x minus y equals 4. Same instructions, so what I want you to do is pause the video and write this down as a matrix equation of the form ax equals b. So you should have -3, 1/2, 6, -1 times the column matrix xy is equal to 2, 4. Now trying to find the inverse of -3, 1/2, 6, -1, we're going to set up the augmented matrix -3, 1/2, 1, 0, 6, -1, 0, 1, and try to perform row operations. What we're going to find is that A inverse does not exist. This was also in a previous video. So I'm writing A inverse D and E. It's not an invertible matrix, which means this system either has no solution or it's dependent. In order to find out which, what I now need to do is go to previous techniques. And so I'm going to take the first row and multiply it by 2. I get -6x plus y is equal to 4. And 6x minus y is equal to 4. And when I add those two together, I get that 0 is equal to 8. This is a false statement, and so this system has no solution. Suppose our initial system had been -3x plus 1/2 y equals -2, and 6x minus y equals 4. If that had been the case to begin with, then multiplying the first equation by 2 would have given me -6x plus y equals -4, and then 6x minus y equals 4. Adding those two would have given me that 0 equals 0, which is a true statement, and we would have said it's the set of x, y, such that, and then we want to say both of the lines are the same. We want the ordered pairs that are on the line, and so we could pick either of the two equations. I'll pick 6x minus y equals 4. So the set of ordered pairs xy such that 6x minus y equals 4 would have been our dependent solution. What I want you to get from this is, if the inverse doesn't exist, then you have one of those special cases. Next, we have the same instructions, and our system is 3x plus 3y plus z equals -1, x plus 2y plus z equals 0, and 2x minus y plus z equals 4. What I want you to do is pause the video, express the system as a matrix equation of the form ax equals b. I want you to find the inverse of a, and then I want you to solve the system. So my coefficient matrix A is 3, 3, 1, 1, 2, 1, 2, -1, 1. My variable matrix, column matrix X is X, Y, Z, and then the product of those equals the column matrix 1, 0, 4, those constants, right? So I have that A is 3, 3, 1, 1, 2, 1, 2, -1, 1. And so I would set up an augmented matrix with those numbers on the left and the identity matrix on the right, and then perform row operations, which we did in a previous video. I know, so efficient, isn't it? What we found in that previous video is that A inverse turned out to be 3/7, -4/7, 1/7, 1/7, 1/7, -2/7, and -5/7, 9/7, 3/7. And so that's our A inverse. I'll just write it and not say it all again to spare you. And since our original matrix equation is of the form AX equals B, and what I want to do is multiply both sides by A inverse on the left, what I'm really after is, since A inverse times A gives the identity matrix, I'm really after being able to construct the equation X is equal to A inverse times B. X is the column matrix X, Y, Z. A inverse is this matrix with all these fractions that we've already heard and seen. And B is 1, 0, 4. Now what we need to do is perform the indicated multiplication. And so we need to take that first row, 3/7, -4/7, 1/7, and multiply it by 1, 0, 4. Then we need to take the second row, 1/7, 1/7, -2/7, multiply it by 1, 0, 4. And then the third row, -5/7, 9/7, 3/7, and multiply it by 1, 0, 4. The result is going to be X, Y, Z. Oh, I'm not going to tell you just yet. Go ahead and pause the video and figure out what your answer is. When all is said and done, I get that X, Y, Z is equal to 1, -1, 1. I've written that as in matrix form. I really want it as an ordered triple. So X, Y, Z, commas, parentheses is equal to 1, -1, 1, which you should most certainly check in the original system of equations. But again, this is how matrix equations are solved using the inverse of a matrix.